Hi, sorry. I was having slight technical difficulties this morning. Okie dokie. Thanks for being here. Okay, today we're going to do a long FRQ. It might be one that takes beyond our time this morning, just to make sure that you feel like it's just right and you have everything you want down on paper, so that if this, pops up as a real FRQ during the AP, you have, lots to choose from, lots of great sentences to grab. This is one of those ones that, you really, there's a good chance that even if you don't, it's not exactly the same, you're going to use one of these sentences that you create today. So that will definitely fill another need later on in the AP. So taking our time on this one a little bit and making sure we have all of the options possible down on paper, I think is going to be beneficial. Let's see, I'm not going to send it to you because it's kind of short. You should be able to jot it down. So I'll share my screen. You can give it a quick copy and we'll talk about it a little bit. Let's see. But now I have to remember where I just put it. Hello. There we go. Okay, so this one says, it looks like it wouldn't be a long FRQ, right? Because it just looks so little, but it is a long FRQ. And it's because it gets a little wordy within these three categories, but let's talk about it. It says, scientists seeking to determine which molecule is responsible for the transmission of characteristics from one generation to the next knew that the molecules must, 1, copy itself precisely, 2, be stable but able to be changed, and 3, be complex enough to determine the organism's phenotype. So, spoiler alert, obviously we're talking about DNA here. It says, explain how DNA meets each of the 3 criteria stated above. So DNA is the focus molecule. Basically, in this long FRQ, you're talking about how great DNA is. Why is it this super molecule? Well, it's because it can do all 3 of these things. And within each of these 3 things, there's lots of reasons why it does it. It can do these things, 3, 4, 5 times over within each of these categories. So do you need to name everything it can do within each category? No, not at all. If you have one example from each of these categories, you're in good shape. However, this is one of those rare occasions where it doesn't tell you exactly how many things it wants you to say. It could say, explain how DNA meets each of these 3 criteria with 1 example, or give 2 examples how DNA meets each of these 3 criteria. It doesn't give us a limit this time. That's the clue that this is a long FRQ, that they want to know everything you know about this one. So will you get marked down if you have less? No. Will you get more points if you have more clear, concise reasons? Maybe. So this is the one where it's kind of open-ended and it's long, so they're expecting lots of good stuff out of here. Okay, so let's see. Other than the fact that our one task verb today is explain. And remember, explain is just, be clear, be concise, be plain and simple for your grandma, your little brother, your mom who knows nothing about DNA. We're trying to make it really clear what this molecule can do. Okay, so you don't have to paint some beautiful picture like we would when we're describing and storytelling, because especially with DNA, that can go down a rabbit hole, right? This is pretty clear and concise. You can use vocabulary terms. If you feel like some of them are not clear, define the vocabulary word, remember? And then we can definitely go over these, and you can always send them to me afterwards too, because this is where we tend to, maybe get lost in a little word jargon, and the more clear and concise and easier your answer is for your reader to find, the better. Keep yourself organized when you're working on this one. So if you're going to break it up into the 3 different criteria stated, break it up with a space between the paragraphs, or break it up by underlining what you're talking about, so that they can really find what you're trying to get across. Okay, I'll leave you alone. I'll leave this up. It is a long FRQ, so I won't check back in for at least 10 minutes. And then we'll see how we are, okay? Have fun. DNA, everything you know about DNA. Okay, we're creeping up on just a little over 10 minutes. So I'm just checking in on you. I don't expect you to be done by any means, but anyone have any questions so far or any clarification on anything? Definitely more time though, right? Sort of, okay. Anybody else down there? Thumbs up, thumbs down, need more time. It's very quiet. I'm guessing you're working hard, so I'll just give you some more time. Okay, we're just creeping up on 20 minutes. So if I could just get a little check-in here, how we doing? Can you just let me know if you need more time?
Two more minutes.
A couple more minutes? Yeah, no problem.
I'm just finishing up, so
Okay.
whatever is good.
Okay. Michaela, Moira, how we doing? Moira's done.
Yeah, I need a little bit more time.
No problem. Just give it a couple more minutes and then we'll talk about it. Okie dokie, let's go ahead and start our chat because it'll take us a little bit to get through all of the points for this one. And just know that you can always be adding on to this so that it's, you feel like you have lots of different options and complete sentences to pick from later on. So when you're putting things at the top of the pile for Unit 6, this should go pretty close to the top because it's got a lot of great points in it, a lot of great little sentence grabs that may come into play for other questions. I can totally see, a different FRQ just grabbing a quick question about, the stability of DNA or, what makes, phenotype possible or something like that. So this is a great one to have lots of good sentence grabs from. So, okay. Let me just throw the question up just because, why not? When we're talking about characteristics of an awesome molecule, scientists believe that it had to be able to copy itself precisely. It has to be super stable, but also changeable. And it has to be complex enough to determine something's phenotype, be able to change the way something looks or acts. Okay, so how does DNA fit all these criteria? Basically, it doesn't give us any kind of limitation, so you could talk on and on and on as long as it's concise and clear for your reader about DNA for each of these criteria. So let's start with copying itself precisely. How does DNA copy itself precisely?
I put that its replication is semi-conservative.
Okay, say more things like that. What do you mean?
Like a new strand will have one of the template and one of newly synthesized DNA. So it contains like original DNA and new DNA. It's not just all new.
Perfect. So Sadie's actually hitting on multiple things in one sentence. The key one that I'm picking up from what she's saying is that there is a template. Yep, so that's what she means by it being semi-conservative, is that one piece is the original and the other piece is the copy or the complement to it. So perfect. That is one way that it is able to copy is because it keeps a hard copy all the time. There's a template strand, and that's how we get, perfect copies every time.
Kind of going off of what Sadie said.
Yeah.
I talked about how like the complementary bases, I wouldn't really call them complementary, but like the matching base pairs, like the nucleotides, how like A has to pair with T
Perfect.
and G pair with C.
Yes, exactly. So the fact that its molecular structure has, matching components that, create some kind of code. So if you talked about complementary base pairs, A's binding with T's and G's binding with C's, that they kind of look alike. Maybe you even went as far to talk about, oh my gosh. Well, clearly I need more T to make my brain turn back on. Maybe you went as far as to talk about the two groups of base pairs where A's are like C's and G's are like T's. And Miss Masonet's going to think of this term. Oh my gosh, you guys. Okay, now it's up to you.
Purines and
Thank you. Purines and pyrimidines. Thank goodness somebody's awake. Right, so maybe you want to start to talk about those as well, as far as chemical structure. Great, Michaela, thank you. Anyone else have another one? So far we've got molecular structure and complementary base pairs, and we've got its complementary strand and that there's a template, okay? Anyone else have any different ones?
I pretty much had the same exact thing. So
Okay, great, okay.
yeah.
I also put that you can repair it.
Yes, it's repairable, totally. Yeah. Yeah, I would just, as far as, you know, it being copied precisely, right? So if we're still thinking about how it's copied precisely, that it's repaired, I would just say, yeah, repairable is great. That's a great term. Maybe just adding that enzymes are available, or other proteins or molecules are available to help repair it, that DNA itself doesn't, I mean, it's repairing itself because it holds the code for the enzymes that then repair it. So yeah, it repairs itself. Great. Let's see, we got that one. Okay, the only other ones that I had down that maybe you want to just jot down to write a sentence about later would be that there are enzymes that help it do the copying, like DNA polymerase. And enzymes that help open up the DNA so that that template strand can be copied. So I just wrote the word unzippable. That's definitely not a science word.
Do we have to list them as enzymes? Like, I mentioned the enzymes like helicase and like I don't know how to pronounce that, topoisomerase and DNA polymerase. Like, I mentioned those, but I didn't call them enzymes. Like, do I have to like specifically say like this enzyme?
I might say that. I might say enzymes like DNA polymerase, helicase, etc., are there to help unzip, you know, build the DNA complement strand and repair DNA or something like that.
Okay.
I always revert back to, especially with explain, I always revert back to sitting next to Granny. And if I said any of this to Granny, she'd be like, Hela, who? DN, what? So, I mean, if, you know, just giving her a couple extra words that maybe Granny's heard before, like enzyme or something like that, might help her a little bit. Again, the people that score the AP are biology teachers, whether they're college or high school or both. So in theory, they're going to be very kind and know all these words and know what you're talking about. But they also don't want to have to hunt for it, you know? But I think that's great. Okay, so I think that's it. We talked about template strand, we talked about DNA structure, DNA polymerase, other enzymes that help repair it, the fact that it does unzip. So I think we got them all for copying itself precisely. Now, some of those may be repeated in the next two characteristics. So just know that that's okay. So let's move on to the second one. How is DNA stable, but also changeable?
I said it was stable because of its double helix shape, and then
Ah,
its double helix shape is as a result of like the multiple H bonds that it has within it.
yeah, absolutely perfect. You
So,
nailed two of the big ones, right? So it's stable because it's a double helix, and it basically closes that complement or that template strand into itself so that it's protected. It's got a strong sugar backbone, and then it's got hydrogen bonds that hold the two strands together. Now, hydrogen bonds, we know of all the bonds that those are the weakest bonds, but they're important to keeping DNA together while it's packaged safely in the nucleus until it's coming to be unzipped. So easily made, easily broken kind of thing, I guess you could say, because it makes it nice and tight, but at the same time, easy to unzip and make a copy of. So great, Xander, perfect.
Could you mention the hydrogen bonds for, whatchamacallit? Oh, wait, hold on. Could that be a reason for why it's easily changed?
Oh,
because
absolutely.
It's easily unzipped
Yeah.
and
Yes, absolutely, because when you go to unzip it, hydrogen bonds are easily broken and reformed. That's a perfect reason for why it's also able to change. Yep, love it. If you manage to get both of those things, making it stable and changeable with hydrogen bonds in one sentence, awesome. As a reader, I'd be like, yep, you got it, you get it, 5 points. Okay, other things? Stable or changeable?
I said it was like, I guess, changeable because of like a mutation in the sequence, right?
Yeah,
So like a
100%.
substitution or like insertion, I guess you could
Yep.
say. And then I also said, I guess like the base changes as well. I don't know. I was kind of like trying to find a second one on that one.
You're absolutely right. So mutations to the DNA are possible. Just at baseline, that's a great answer. You went even further to talk about insertion or what's the other one you just said? Oh, my brain.
Base changes, sorry.
Oh yeah, so SNPs, so like single nucleotide polymorphisms, are all great ways in showing that it's changeable at the base pair level. Good? Great, great, great.
Yep, sounds good. Thank you.
Yeah. Anyone else before I go over some more that you can just jot down to write about later? Okay, I'm just gonna give you a couple more to jot down. So as far as things that make it stable, DNA, I mean, I wrote tricky. That's again, not really a science word, but maybe helps to paint a picture. It's tricky because it has introns and exons within its code, that not all of the DNA is super crucial to the organism. So in that way, it makes it more stable because it doesn't, you can mess up a bunch of introns and it won't matter. It's the exons that are super important. So that helps make it stable. This is the same thing as what we talked about in copying itself precisely in the first characteristic. And I think it was Sadie that mentioned it, but it's repairable. Enzymes can come around and repair it. So that makes it more stable. Some things that make it changeable that we didn't mention. Xander is on the right track with this. He mentioned, point mutations or insertions, but in addition, other things that can mutate base pairs are, environmental effects like UV radiation or chemical changes can mess up the DNA, or a virus or a bacteria can come in and mess up DNA. So the fact that it's sensitive to those things still, even though it's so stable, make it give it the criteria to be changed. And then if a long strand of DNA gets close enough to another strand of DNA, it likes to trade sometimes. Hey, you want to trade a little piece? And we get what's called crossing over. So that's another way that it's able to be changed. Okay, so I think we got them all then for the second criteria, which is it is stable, but also changeable. Any questions about that one? Okie dokie. The last one is that it is complex enough to determine an organism's phenotype. So how is DNA so cool that it can make us all look different?
I talked about transcription and translation.
Yeah.
And how proteins are made, and basically the proteins are what makes the phenotype.
Yeah.
So like black hair has specific proteins that make your hair black.
Exactly. Yep. Perfect. I mean, the transcription and translation part of it is like the key, right? That's what that process is what's so complex that we get so many variations in phenotypic outcome for all organisms. So definitely mentioning transcription translation as a process. In general, what are those doing? Anyone else have something else?
I kind of put like along the same lines, I put that nucleotides code for 21 different amino acids that can be put in, I don't know, like infinite combinations.
Exactly. Yep. Yeah. If you're just mentioning what DNA is at its core, which is a code for amino acids, and amino acids make proteins, and proteins are what do everything and function and create these phenotypes, then you're on the right track. And that might seem kind of, rudimentary or elementary as far as describing DNA, but that's what they're getting at. They just want you to know that, hey, DNA is, it's got so many different options because of its code. And that the fact that it then codes for something that's going to do a function, that's what makes it so awesome and complex enough to make phenotypes. Good. Anyone else? I mean, you pretty much got them all. I mean, you could have gone into smaller detail about some of them, just talking about, again, like if there's any variation in the sequence, that creates variation in proteins. So just using those kind of words like variation, obviously, Jayla mentioned transcription and translation, coding, amino acids, endless possibilities of the different combinations of proteins and amino acids. And that's what makes us different. Okay, questions on this one? Probably not too many, I'm guessing, because we're very familiar with DNA. We've been talking about this molecule since the beginning of time, but you may, find it difficult to, create lovely, concise sentences to convey what you mean. So that's the challenge of this one, is making sure you're clear and concise and organized so that your reader doesn't have to search for what you mean. And then, keeping this one at the top of the pile, because I can almost guarantee we're going to want to grab some of these sentences later. Feel free to send them my way. I'm almost caught up on FRQ feedback, so today would be a good day because I don't have any other Zooms today and I can get a bunch done. Send them my way if you like. Otherwise, great job, and we'll see you soon, I guess. Okay, all right. Have a great day, you guys.
Thank you.
You got it.
Thank you.
Yeah.